Let's do some more examples of area between curves. All of these involve trigonometric functions. We're asked to find the area of the shaded region bounded by y equals secant squared x and y equals 8 cosine x. We do have the graphs drawn and the region shaded, but we don't have indicated which graph is which. So we have to have some prior knowledge about at least one of these two trig functions. And so the graph of y equals 8 cosine x graph starts at the amplitude when x equals 0. So that means that this downward facing piece here is going to be the portion of y equals 8 cosine x, which means that the other function must be y equals secant squared x. And that's not really a basic function. We wouldn't know exactly what that looks like, but by process of elimination, now we do. So we clearly know which is the top and which is the bottom function, but what we're missing is when these two graphs intersect. So we're going to have to solve 8 cosine x. When is that equal to secant squared x? All right, well, we know that secant x is 1 over cosine x from our trig identities. So we have 8 cosine x is equal to 1 over cosine squared x. And then we'll go ahead and multiply by cosine squared x, and then I'm going to divide by 8 at the same time. So I end up with cosine cubed x is equal to 1 over 8. And to get cosine x by itself, I will take the cube root of both sides, and that's going to leave me with cosine x is equal to 1/2. Works out quite nice. Now, solving for what angles do I substitute in to x to get into cosine to get out 1/2? Well, the main angle I'm thinking about is x is equal to pi over 3. And there's infinitely many solutions to this trig equation here, but just in the interval from 0 to 2 pi, so around the unit circle, we're looking at pi over 3 and 5 pi over 3. But actually pi over 3, just knowing that is enough because that's going to be the first positive value here. So we know that this point of intersection, this positive one, is going to be pi over 3. And because of symmetry, this value over here is going to be negative pi over 3. And that's enough to set up and then find the area. So we're going to have the area between these two curves is going to be the integral from negative pi over 3 to pi over 3 of the top function 8 cosine x minus the bottom function secant squared x dx. Because we're actually going to go all the way through and find the area, if possible, we should try to use symmetry to our advantage for solving. So this integral is actually equivalent to just finding the integral from 0 to pi over 3, so this area on the right side here, and then doubling it. So we can go ahead and say this is the same as 2 times the integral from 0 to pi over 3 of the same integrand. And it's always easier to substitute 0 in usually. So we're going to go ahead and now find the antiderivative and each one separately. So we're going to have 2 times the antiderivative of 8 cosine x is 8 sine x. And the antiderivative of secant squared x is tangent x. So we have minus tangent x, and we're evaluating this from 0 to pi over 3. So we'll plug in pi over 3 first. So we'll have 8 sine of pi over 3 minus tangent of pi over 3 minus, if I plug 0 into sine x and tangent x, luckily both of those do end up being 0. So it was worth it to use symmetry because it's nice that this is just going to be minus 0. So we have 2 times 8 times the quantity 8 times sine of pi over 3, that's radical 3 over 2. And tangent of pi over 3 is radical 3. And it's going to be pretty nice here. We're going to have 4 rad 3 minus rad 3 in the parentheses there, which is 3 radical 3 times that 2 in the front. So we have a final answer of 6 radical 3. And because it's area, it would be units squared if units were provided. In this example, we're just going to set up the integral to find the area bounded by y equals cosine x and y equals negative sine x between x equals 0 and x equals pi, and we want to sketch the region. Here we are not given the graphs. They are really basic trigonometric functions. So cosine x does start at the amplitude. It starts at 1, and then it's going to go down from there and form that periodic function. So we'll start with that. Here's our graph, and notice that our tick marks are the quadrantal angles pi over 2, pi, 3 pi over 2, 2 pi. And then y equals negative sine x. Sine x starts at the origin and then normally starts going up, or is an increasing function, but the negative is going to be a reflection over the x-axis, so it's going to start heading down. So here is our negative sine x function, and we're looking for the area bounded between these two curves, but only between x equals 0 and x equals pi. So the region that we're talking about here starts out with cosine x on the top and negative sine x on the bottom, but they are going to switch before we hit the end of the interval pi, and then this negative sine x is on the top and cosine x is on the bottom. So what we need to do is figure out at what x value they intersect, because there is a different top and bottom function over the interval. So we have to set these two functions equal to each other. If I solve cosine x equals negative sine x, I'm going to divide both sides by cosine x. So I'll get 1 equals negative sine x over cosine x. Well, that's just a negative tangent x. So I'm actually going to divide by negative 1 and end up with negative 1 is equal to tangent x. And so now let's think about the solutions to this equation just on 0 to 2 pi. So tangent is negative in quadrants 2 and 4. So we're going to go ahead and say that our x values there, where tangent is equal to negative 1, is 3 pi over 4 and 7 pi over 4. Well, if we go ahead and take a look, we can see that the x value where they intersect is going to be that 3 pi over 4 value. So we're going to have our two integrals. We're finding this first region's area here. So we're going to have area is the integral from 0 to 3 pi over 4 of the top function. First is cosine x minus the bottom function, negative sine x. So ultimately that's going to be cosine x plus sine x. Plus, we're adding a little bit more area here, the integral from 3 pi over 4 to pi. And this time we're going to have negative sine x minus cosine x. So those top and bottom functions switch. And sometimes it's nice if you're able to use color to distinguish between the two curves, because we could see the top one was blue and then the bottom one was pink, and then it switched from pink on top to blue on the bottom. So some indication of color or maybe thickness of line to distinguish between the two and help us identify when we're going to need two separate integrals. Now let's set up the integral to find the area bounded by y equals tangent x, y equals 1, and the y-axis. So let's start by sketching the region. We need to set up a grid, and then we'll start by graphing y equals tangent x. So we know the general shape of tangent x, and we'll notice that the other pieces are y equals 1 and the y-axis. So we're going to go ahead and kind of just zoom in on the tangent x graph, and I'm going to sketch just this part of it in quadrant 1. So here is a rough sketch of y equals tangent x. It does have a vertical asymptote on the right side of the y-axis at pi over 2. And another key value we should know is that at pi over 4, tangent of pi over 4 has an output of 1. So we should definitely graph tangent x first, and we should identify that key point, especially because the other equation is y equals 1. So that's just a horizontal line right there. And then the last equation is the y-axis. All right, so the region that we're trying to find the area of is this region here, so bounded by these three equations. And so we can set up the integral with respect to x. There is a clear top and a bottom function. And because we already identified that tangent of pi over 4 is 1, we do have x limits of integration. So we can go ahead and set up our area in terms of x by setting up the integral from x equals 0 to x equals pi over 4 of the top function. Well, that is 1, just the horizontal line 1, minus the bottom function, tangent x, dx. And that's perfect, that's fine, there's nothing wrong with that. But just for the extra practice, we're also going to set it up in terms of y. So we can say that the area can also be found doing the integral from y equals 0 to y equals 1. So we're looking at limits of integration from the y-axis. But then we're going to have to do right minus left. And there is a clear right minus left. The right function, right, is the curve, and the left is the y-axis. But we have to be careful about the curve y equals tangent x. It's a function of x. So we'd have to rewrite it to be a function of y. Well, what happens is it just becomes x equals tan inverse of y. So then when we do right minus left, we're going to have tan inverse of y minus 0, which is just tan inverse of y dy. Now, because the problem was set up, I really think the difficulty is about the same in the setup, but let's just think about if we actually had to find the area. So the integrand here, 1 minus tangent x, we can take each one separately, and each one is not too bad to integrate. 1 is obviously very easy. Tangent x, a lot of people memorize this result, or we can find it using a u substitution. So this one here, it was only one term in the integrand, but tangent inverse of y, or arctangent of y, actually requires the integration strategy by parts, so it can be a little bit trickier. So the area setup wasn't too bad in x or y, but in x, it's easier to integrate. So just something to think about when you're asked to actually find the area bounded by some curves.